Okay, so welcome everyone to the Extreme Universe Colloquium. Today it's my pleasure to introduce a speaker, Robert Koenig, Professor Robert Koenig, from the Technical University of Munich. Um, Robert has made a number of important contributions to many fields in many areas in quantum information, including quantum communication theory, fault-tolerant quantum computing, quantum computation, as well as quantum many-body physics. Um, so to tell you a little bit about Robert, Robert did his PhD, he completed his PhD in 2007 at the University of Cambridge. He then worked as a postdoctoral researcher at Caltech and, um, and the IBM T.J. Watson Research Center. After that, he became an assistant professor at the Institute for Quantum Computing at the University of Waterloo before moving to the Technical University of Munich, where he is now a professor. So today, Robert will be telling us about quantum fault tolerance and locality. So take it away, Robert.
Okay, thank you very much. Thanks for the invitation to speak here. It's a great pleasure. I would like to tell you a little bit about joint work with my student Shinho Choi. I think this is representative of the kind of research we do in our group here. So my research field is, as Andrew has already mentioned, quantum computing. And of course, we have various different ideas of potential applications of a universal quantum computer. But today I will not talk about these applications, but instead I'd like to discuss the question of how we can actually build such a fault-tolerant device. But let me start at the very beginning. So what do we like to do in quantum computing? So here's the circuit model for quantum computing. We start with n qubits, the tensor product space of n two-dimensional spaces. We have an orthonormal basis, which we call the computational basis. And the computation usually starts with us initializing the state of the system in one of these computational basis states. So diagrammatically, we draw n lines for these n qubits, and this is the initialization step. The next thing we need are gates. These are evolution operations, so norm-preserving maps on this Hilbert space. And these gates can be specified by giving their action on computational basis elements. So here are three examples. What's important about these gates is that they can be applied simultaneously if they act on disjoint subsets of qubits. So here are three examples, and the corresponding operators correspond to tensor product operators, where we have identity factor when we don't have a gate on a certain wire. The last element we need are measurements. Measurements turn a state into a sample, a bit string, from a distribution given by the modulus squared coefficients of the wave function. So diagrammatically, they will be represented in this way. So we have a state going in, and we get a bit string out of this measurement. So here's how the computation proceeds. We start with the input state, we apply a series of gates, and at the end we measure the state, and we get a certain bit string output. Now, let me just emphasize that the whole functionality of the device that we use for computation, for example, is captured by this conditional distribution, and this is basically determined by Born's rule. Let me also introduce one important concept for this talk. So this is the depth of a quantum circuit. This is basically the number of so-called gate layers you need to apply. It's a measure of the amount of time you need to apply the circuit. In each gate layer, we have gates acting on disjoint subsets of qubits, so they can be applied simultaneously. And then depth is the number of such gate layers. Okay, so let me address one basic question, and this is the question of which gate sets we should be using. basically we would like to be able to apply any unitary on n qubits. And the answer is given by something called the Solovay-Kitaev theorem. Basically, what you need to be able to apply is a so-called universal gate set. A universal gate set is a family of unitaries that generates a dense subgroup in the unitary group on n qubits. So examples, I mean, the way this theorem works is that it really gives you an algorithm for taking an arbitrary unitary and compiling it into a series of gates from your universal gate sets. So here's a formulation for a single qubit and this universal gate set. So what are examples of universal gate sets for a single qubit? You can use, for example, rotations around the x or z axis with arbitrary angles of rotation, or you can use these two gates, h and the so-called pi over 8 gate, to get a universal gate set. Let me also introduce two gate sets that are not universal here. So important for quantum computing is, of course, the Pauli group. So these are just tensor product of Pauli operators on individual qubits. And we have the Clifford group, which is the normalizer of the Pauli group inside the group of unitaries. So it's the set of unitaries that map Paulis to Paulis under conjugation. Both of these groups are finite groups, and this is why they cannot be universal gate sets. But they will still be important in quantum computing because they're generally easy to apply in, for example, a stabilizer error correcting code. So you might wonder, how do we get such a non-Clifford gate, such, for example, the pi over 8 gate? And one trick that has been discovered and that is very important is something called magic state injection. So here the idea is that we use a certain resource state, this particular so-called magic state here, and we use operations from the Clifford group. So basically, these are just Clifford unitaries, computational basis measurements, and this denotes a controlled S gate. So depending on the measurement result, we apply this Clifford or we don't. And it turns out that if you do this kind of circuit, you actually realize this T gate. So one thing you can say is that instead of talking about universal gate sets, we could also talk about these three operations. And if you combine them correctly, you can basically realize an arbitrary unitary. And this is what I'm going to do. I'm going to use this single state preparation and this single and two cubic Cliffords and measurements in the computational basis as my building blocks to generate larger circuits. I would also like to emphasize that this is an example of what we call an adaptive circuit here. Adaptivity means that we have mid-circuit measurements and the measurement result is used in the further computation. So here to decide whether this S gate should be applied or not. More generally, an adaptive circuit could look something like this. We have a series of unitary gates, and then we might have some measurements. And these measurement results are then used to determine what gates to apply subsequently. This determination involves some classical computation, and throughout this talk, I will assume that this classical computation is efficient. In particular, this should be done on a timescale which is much faster than the timescale of these individual gates. So correspondingly, I will define the notion of the depth of an adaptive circuit in this way. So I actually use the same notion when we just have unitary gates, but when we have these classical computations, I will just call this a depth 1 step. So this is a gate layer which now involves efficient classical computation and application of a depth 1 quantum circuit. So here we have several gate layers. This is not the only possible definition of circuit depths, of course. You could, in principle, also think about the circuit depths of this classical computation. But for the purpose of this talk, I will assume that depth of classical computation is not counted in this precise manner. So I will only talk about, in some sense, the quantum depth of the circuit. Okay, so let's look at what we need to describe this adaptive circuit. Basically, in every gate layer, we have these three types of operations that are applied. Here's the next gate layer, and so on. And so one thing you can say is that we have a pairing of the qubits in each gate layer. This pairing tells you where you apply 2-qubit operations. We can combine 1-qubit operations into 2-qubit operations. So in each gate layer, you have a pairing of the qubits. And then additionally, you have to say what operations you're applying to each pair. So we can say that an adaptive circuit is given by T layers. Each layer has a pairing of the qubits associated with it. And for each pair in this pairing, you have a 2-qubit operation. And we're looking at the tensor product of these that are applied simultaneously. So this is sort of the formal description of an adaptive circuit. Okay, so now let me actually get to the main topic of this talk. And the question now is, how do we actually run such circuits in the real world? One thing we haven't talked about so far is that these circuits are generally noisy, the ones that we have in the lab. And also we have locality constraints. So these are the main issues that we have to deal with. And this is basically the topic of this talk. So let me first talk about locality. So here are 3 examples of different device architectures from 3 different companies. And usually they give you this kind of graph. This graph tells you where the qubits are and which of the qubits interact with each other. In other words, where you can apply 2-qubit operations, for example, 2-qubit unitaries. So for example, in this case, you cannot apply a 2-qubit gate between qubit 113 and qubit 13 because they're far from each other. You can only apply nearest neighbor gates on this graph. And somehow we have to take this into account when trying to run algorithms on such devices. So the way I'm going to represent this is by graphs like this. So if we don't think about locality, then we're dealing with this complete graph. So we can apply any 2-qubit operation between any pairs of qubits. On the other hand, in practice, we usually have limited connectivity, which is going to be displayed by a graph like this. So we have, for example, only nearest neighbor or next to nearest neighbor interactions between qubits. And the question is, can we simulate a device that has full connectivity using such a limited connectivity device, and how to do this? The next obstacle we have to deal with is noise. Noise can affect any component in your circuit. This can affect preparation of initial states, measurements, and unitaries, but also so-called wait locations where qubits just sit around and wait for the next action. So this we're going to have to discuss in detail. So what do I mean by noise, for example? Okay, so here's again an overview of the goal of this talk. So the idea is we have an ideal circuit. Think of, for example, short circuit. And we would like to run this circuit on a device that has low connectivity and is noisy. And the question is, how can you recompile this algorithm, for example, Shor's algorithm, into an instruction set that can be run on this low connectivity device that's noisy in such a way that the results can be used to basically simulate this ideal device. This is basically the goal. And this is why I'm drawing the arrow in this direction. You might think it would also be natural to draw it in the other direction. But typically, we have some ideal circuits we would like to run. And then we ask, can we realize this using a low connectivity device? And this is procedure. And the way we're going to approach this is by breaking this problem down into 2 steps. So the quantitative questions we would like to answer here, of course, are how many additional qubits will we need? Typically, we need more qubits to achieve fault tolerance. And perhaps we also need more time because we have to do fault tolerance operations. So we want to quantify how much additional time is needed. So this is sort of the quantitative question that we're trying to answer. We would like to give procedures that are efficient in regards to these two metrics. But now to approach this problem, we are going to use a two-step reduction. So the first question we might ask is, can we simulate an ideal fully connected device using a noisy device, which is still fully connected? So here we're ignoring locality constraints. We just want to design fault tolerance schemes, error correcting codes, and so on, that allow us to simulate such an ideal fully connected device that is noise-free using a noisy device. And it turns out this is a very well-studied problem. I mean, this has a very long history, and we can simply use results that have been obtained in the past. So they're beautiful fault tolerance constructions that achieve this reduction. And I will mention one of the most recent ones, but I cannot do justice to the whole field. This is a basic and very well-studied problem. What we focus on is this second step in this reduction. We ask, how can we simulate a fully connected noisy device using a low connectivity noisy device? And in this setup, everything is noisy. We're not trying to simulate an ideal circuit. So that means that we also not aiming for a perfect simulation. All we want is that the noise here basically translates into a certain amount of noise on the left. So we construct what I call a noise-robust localizer, kind of a recompilation procedure, which takes a prescription, a circuit in this setup, to a circuit in this setup, in such a way that a noisy execution of this new circuit will be equivalent to a noisy execution of this circuit. So this is basically our main contribution. And when you put this together, you get, first of all, a conceptual insights. Basically, what this means is that you can really separate this fault tolerance aspect, where you try to get from noisy to ideal, from considerations related to locality, where we're trying to go from fully connected to low connectivity. But the practical implication is that we really have a reduction. So we have these two components, but if you put them together, we get an overhead efficient fault tolerance construction, or several such constructions, which incorporate locality. So we can take a known construction and add this locality by our procedure. So this is perhaps the main application. Okay, so let me mention one of these fault tolerance constructions. So this is the arrow that I had on the left. So we try to simulate an ideal device using a noisy device. And this is an example of a so-called threshold theorem. It is really a state-of-the-art theorem that has the best parameters. This is a recent result by Yamazaki and Koashi. So what does this say? It says that if you have an ideal circuit that you would like to run, let's say it has n qubits and depth t of n, then you can construct a fault-tolerant circuit. The circuit is slightly larger. It has a constant factor more qubits. This is something we call the overhead. So the qubit overlap head is constant. This is considered small. I mean, it's as small as it basically can be. And it's also slightly deeper. The depth increases by a factor, and this is a function which we call quasi-polylogarithmic. But again, this is considered small. It's at least the best known construction in terms of this depth overhead. So we go from this ideal circuit to a fault-tolerant circuit, which is slightly larger. And this fault-tolerant circuit, it has the property that even if you can only implement it noisily, as long as the noise strength is below some threshold, you get an approximation to the output distribution of this ideal circuit. So this is called the noise tolerance threshold theorem. it tells us that if the noise rate is below a threshold, we can simulate the ideal circuit using this fault-tolerant circuit, even if the fault-tolerant circuit cannot be perfectly implemented. So I will tell you what I mean by noise implementation and so on, but that's the basic idea of such fault tolerance constructions. So this is a nice construction, but one thing I should perhaps add here is that, in fact, the result of Yamazaki and Koashi is stronger than stated here. It's stronger in the sense that it actually also takes into account the time it takes to do the classical computation. So they use a different notion of circuit depth, which also takes into account efficient classical computation. But for the purpose of this talk, I would like to neglect this distinction, and we're really using this simplified notion where classical computation, efficient classical computation, is essentially considered to be free. So our improvement, if you like, to this result is to make the construction local. So here we're using non-local gates also in this fault-tolerant circuit. We would like to simulate this ideal circuit using a noisy device with low connectivity. And what we can do is we can give a 3D local circuit which achieves this. What do I mean by 3D local? It means that the qubits are arranged on a grid graph of this shape. And our circuit only uses operation between neighboring pairs of qubits, so a sequence of gates that could look something like this. The claim is that we can again take the ideal circuit and recompile it into a fault-tolerant circuit whose execution simulates the ideal circuit for noise below a threshold. But here we need more qubits. We need a polynomial overhead in the number of qubits, but we can preserve this depth overhead. The depth overhead is still quasi-polylogarithmic. And this is perhaps the main achievement of our work, is that we have a local fault tolerance construction whose depth overhead is quasi-polylogarithmic. Okay, so in the remainder of the talk, I would like to explain some of these reductions. And I will start with perhaps the most intuitive part. And this is the question of how we go from a connected device to a low connectivity device. And in fact, I would like to first talk about a simplified version of this where we don't have noise. So we have a fully connected ideal device that we want to simulate, and we want to run this kind of corresponding circuits on a low connectivity ideal device. So let me formalize this slightly. So suppose we have a graph, as I showed you before, that corresponds to the device. We have a qubit in each vertex, and we have, let me call a certain subset of these qubits the computational qubits. Now, operationally, what we can do is we can do nearest neighbor gates on pairs of qubits that are neighboring on this graph. And what we like to do is we like to run an ideal circuit on these computational qubits. So here's the input. So suppose you just look at the gate layer, then we have a pairing of these qubits, of the computational qubits. We would like to apply a 2-qubit operation to this pair, and to this pair in this example. And the question is, how can we apply this if we can only do nearest neighbor operations? So here's a one-dimensional example. And the first idea you might have is that we can simply swap the qubits. And this is a natural approach, and this approach has been taken in prior work on making fault tolerance local. What's not so nice about this approach is that you might need a large number of swap gates, or more precisely, you might need a large circuit depth. By large, I mean something that scales linearly in the number of qubits. And so in that sense, this is not very efficient. It gives you a depth overhead, which is then typically polynomial. So we use a different idea, and the idea comes from entanglement swapping. let me just review this very briefly. So entanglement swapping is the idea that we can generate long-range entanglement using local measurements in constant time. So we have a line of EPR pairs, and we do Bell measurements on pairs of these EPR pairs. And then what we get is a post-measurement state that's a long-range entangled Bell state. And we can figure out which Bell state we have by computing certain functions, efficiently computable functions of these measurement results. So if you think about this as a circuit, it's a constant depth adaptive circuit. We have efficient classical computation and a constant number of operations. So we can apparently generate long-range entanglement in constant depth according to our notion of depth. And this is what we're going to use. So let's modify the rules slightly. So instead of this original graph, let's assume that we have EPR pairs shared between each of these sides of the original graph. And the question is, can we generate entanglements between the pairs that we're interested in? Because once we have this, we can do teleportation to implement non-local gates. So let's say these are our computational qubits, and we have a pairing, and we would like to generate entanglement between this pair and this pair. One way you can do this is if you have edge disjoint paths that connect these points. So the endpoints of these paths correspond to the different pairs in this pairing. If you can find such edge disjoint paths, then you can just do entanglement swapping along this path to generate entanglement between these two qubits and also between these two qubits. And you can do this in parallel for different paths. So this is a very efficient, constant way of generating the required entanglement that you can then use to do teleportation and apply gates. So more formally, we have a certain combinatorial problem. So given a graph, we want to identify a subset of vertices. These correspond to the computational qubits. And we want to be able to apply any configuration of two-qubit operations. So for any pairing of these computational qubits, we want to find edge disjoint paths such that the endpoints of each path corresponds to a pair in this pairing. So if you have such a set of vertices, we can place our computational qubits there, and we have a way of doing these two-qubit operations in constant time. So the question is really, can we find a maximal set of such parallel routable vertices? So here's an example. So if you take a 2D grid, then there is a parallel routable set of size L, if this is an L by L grid. You can, for example, simply use the diagonal, and then the vertices here are parallel routable. If you consider any pairing of these vertices, then you can find edge disjoint paths, for example, this green path and this red path. And in this way, you can show that the set is parallel routable. Now, it turns out if you play around with this configuration, you don't actually have to look at the diagonal. You could also place your computational vertices or qubits here, or here, and here, and you still have parallel routable sets. And what you find is a sufficient condition for this set to be, for a set to be parallel routable. The condition is simply that the projection for each pairing, the projection of these points onto the x or y axis is disjoint. Okay, so as long as you have such a set, you can find edge disjoint paths in this 2D grid graph. Now, we're interested in 3D grid graphs for a reason that will become clearer later on. And what we can show is that in a 3D grid graph of dimensions L by L times 4L, you can find a parallel routable set of size L squared. And the idea is simply to use these vertices on the ground floor. And then we have a greedy construction of a routing for every pairing. So if someone gives you a pairing of these qubits, you can just move pairs of vertices up to different floors, and in each floor you check that the sufficient condition is still satisfied even if you add these vertices, and then you can use the previous routing scheme in 2D. And in this way, we can greedily show that you can parallel route any the subset of qubits. So for any pairing, you can find edge disjoint paths as needed. And this is how this looks like in a concrete example. Of course, not all the paths are shown here, but you can have a pairing of all the qubits in this ground floor and match them up in this way. Okay, and this gives us this reduction that I was talking about. So we want to go from an ideal fully connected circuit to one that has to a device that has low connectivity. And we can use we can do this on a 3D grid graph with an overhead which is polynomial in the number of qubits, and the depth is actually still proportional to the original depth, and we get an exact simulation of the original circuit. So this is a localizer, but it is not fault tolerant in any way, because we're doing entanglement swapping along extensive distances. But this is part of the idea, so we're going to render this fault tolerant. So I talked a little bit about this part. Let me now move on to this left-hand side, and later I will again revisit this part. So I would like to tell you a little bit about fault tolerance in general. And again, this is not our work, but it's prior work by our community, and there have been fantastic developments here over the years. Okay, and so the first question is, how do we formalize the notion of noisy circuits? And the idea is that we can insert additional operators in this circuit, which we call errors. And the natural choice here is to use Pauli errors. There are different justifications for this. For example, you can talk about some process called Pauli twirling, which takes an arbitrary channel and turns it into probabilistic Pauli noise. So this is going to be what we're assuming. And then the next assumption is that we're assuming that high-rate Pauli errors are exponentially suppressed. And this is motivated by physical considerations. The idea is somehow that long-range interactions are successively weaker. And if you make these assumptions, you basically arrive at an error model like this. So this is called a local stochastic error. So what is a local stochastic error? It's a random variable on the Pauli group, and it has the following property. If you fix any subset of qubits and ask, what is the probability that all of these qubits are affected? So what is the probability that the subset of qubits is in the support of the error, where the support is the set of qubits the error acts on non-trivially? Then this probability should be exponentially suppressed in the size of this set, so in the number of qubits we're talking about. Okay, and I will use this notation to denote such a random variable on the Pauli group. So this is a Pauli operator, a random Pauli operator, which has low probability weight on high weight errors. This notion was pioneered by Gottesman in 2014 and used ever since, because it's a very nice and general notion. In particular, it can capture correlated errors because errors on different qubits can be correlated. So if you have IID noise on every qubit, that will be local stochastic, but you can also talk about more general errors. One feature that is nice is that we have a certain calculus of these errors. So for example, if you have two local stochastic errors in succession, then the product is again a local stochastic error. And again, this doesn't require any assumption about the dependence of E and E prime. They can be dependent errors. So we can have correlations not only in space, but also in time. And the second nice feature is that we can understand how such errors propagate under Cliffords, because they're Pauli errors. And for example, you can keep track of the noise strength as you propagate an error through a Clifford circuit. If you have a short depth or shallow circuit, then it will convert pre-existing local stochastic noise into local stochastic noise with slightly worse parameters. Okay, so now I can tell you what we mean by noisy implementation of a circuit. So suppose we have an ideal circuit that we would like to run, then a noisy implementation with error strengths P, the P is missing here, is the following. So we just insert local stochastic errors after each operation. And then the outputs are distributed according to this distribution. What's important here is, again, that these errors don't need to be independent. We're making just an assumption about the marginal distribution of these errors. So whenever I say we have a noisy implementation of a circuit, I mean that we have an ideal circuit, but what we're actually getting is a noisy implementation of this form. Okay, now these fault tolerance constructions, as I said, they start with a general circuit and they give you a larger circuit which simulates the ideal circuit, and the simulation even works if the implementation of this fault tolerant circuit is noisy. And this is the context of this result by Yamazaki and Koashi. Now, this result is based on a very clever use of concatenated codes. And I will not be able to discuss a lot of this in detail, but I would like to talk about some of the components, in particular, the notion of an error correcting code and decoders and so on, to motivate some of our constructions. So in quantum error correction, the first thing that we study is how can we protect against a noise channel. So this is not even talking about computation, it's just preserving quantum information. And the standard approach is to encode our information. Usually this is done using an isometric encoding map. So we're embedding k so-called logical qubits into n physical qubits. And if you do this encoding in the right way, you might hope that you can recover from this noise. So for example, you can undo the effect of the noise by a so-called recovery map. And there are known necessary and sufficient conditions for the existence of such a recovery map for a given noise channel and a given encoding. These are called the Needle-Laflamme conditions. Now, one very popular and very successful approach to building these encoding maps is to use stabilizer codes. So stabilizer codes are basically subspaces of n qubits, and then we use encoding maps that embed k qubits into such a subspace, the so-called code space. In the case of a stabilizer code, the code space is specified by a so-called stabilizer generators, or more generally, a stabilizer group. So we have a group of commuting Pauli operators, and the code space is the simultaneous +1 eigenspace of these operators. And so you can use generators to describe this group, and then you just need to be in the +1 eigenspace of these n-k generators. Now, how does recovery in a stabilizer code look like? The natural thing to do is to measure the eigenvalues of this commuting set of operators, and this generates so-called syndrome. If the syndrome is trivial or 0, then you know that you're still in the code space. So that's a good outcome. But in general, the syndrome will tell you that maybe you're not in the code space anymore. So then you have to apply a correction operation. And this is simply a Pauli operation that depends on the syndrome. And typically we want this Pauli operation to be efficiently computable. This is the decoding part of error correction. So that's a description of the recovery map. Now, just to illustrate this, so this is how this recovery map looks like in the case of the repetition code. In physics terms, you can think of an Ising model of 3 spins here. This is not a very good code in the quantum sense, but we can still talk about these operations. And in this case, the syndrome measurement basically looks at the first 2 qubits and looks at whether they're the same in the same state, and the same for the second 2 qubits. And then you can decide how to correct. So depending on the syndrome, you have to flip either, you have to flip 1 qubit. So this is something called the minimum matching decoder in the setup. So if you fix this decoding map, then you can ask, what is the probability of recovering from this kind of bit flip noise in this process? And obviously, this depends on the distribution of errors you have here. A simple observation is that if you have an overall error, then at least in this setup, you must have had at least 2 bit flips in this error. So either the first and the second bit are flipped, or the first and third, or the second and the third. And in particular, what you can say is that the probability that the recovery fails in this setup is upper bounded by an expression of this form. So this is the probability that the error affects both qubits 1 and 2. This is the probability that we're affecting qubits 1 and 3, and so on. And this is the kind of form we like when we talk about local stochastic noise, because we can, if you have local stochastic noise with parameter p, we can simply upper bound this by 3p squared, because this is exponentially suppressed in the number of qubits. I'm telling you this because this form of upper bound is actually central to our arguments. Let me tell you about the different code, which is the surface code. This encodes a single qubit into an array of qubits. We have a qubit on each edge of this square lattice. This code was introduced by Kitaev and Ravi and Kitaev in the case with boundaries. And it has a polynomial code distance. The distance scales linearly in this linear extent of this lattice. Again, in this case, one can consider the recovery probability using a minimum matching decoder. And you can formally derive a bound which has a very similar form. We're summing over certain subsets of qubits. And what matters is the probability that exactly these qubits are contained in the error. So this has to do with non-trivial cycles, so-called and logical operators in this code. So I'm not telling you what these subsets are, but what's important is that the form of the upper bound means that in the case of local stochastic noise, we just have to evaluate this kind of function. Again, we have this exponential suppression in the size of the subsets. And now you can do combinatorics, and you find an upper bound that looks something like this. And in particular, you see that if the noise strength P is below this threshold, which is in the percentage range, then you can recover from noise. This recovery failure probability will be small if you look at large enough systems. So we see that we can recover from local stochastic noise in this setup thanks to this form of the upper bound. Okay, and so basically this is a kind of argument that we will use. But now I would like to get back to this question of building a noise-robust localizer. And again, so we want to go from this fully connected noisy device to a low connectivity, low noisy device. And if you recall, we first considered the noise-free case, and the main idea there was to generate a Bell resource state, a proper entanglement between relevant pairs of qubits, and then we use entanglement swapping. And the idea up here is now going to be very similar. We are going to create Bell resource states, but in a fault-tolerant manner, and then we use entanglement swapping. So how can we generate Bell states, or more generally, how can we generate stabilizer states? One natural approach that's often used is to apply a certain shallow circuit. So this creates a little bit of entanglement, and then we measure some of the qubits and apply a correction. If you think about entanglement swapping, that has basically this form. We need short-range EPR pairs generated by shallow circuits, and then we measure some qubits to create our desired Bell pair. So we have to discuss fault tolerance of such protocols, and because this is a shallow circuit, we can just commute all the errors in the middle here. So we have to think about what happens when we have an error applied after this shallow circuit. And what we care about is basically whether we get the desired target state. So we should commute this error through. And if you have an error here, it basically implies or is equivalent to an effective error after this circuit. So basically, we get the desired target state up to this error. So now we can ask different questions. We can ask, for example, whether the output state of this noisy circuit is the same as that of the ideal circuit. And this is, of course, only the case if this effective operator is a stabilizer of our target state. If it's not, we get a different state. So the first thing you might ask is, what is the probability that we get the wrong state? So this is the failure probability, and this is simply the probability that this error here after the shallow circuit belongs to this set of errors. And very often we can again bound this failure probability in a similar way as before. So let me introduce a certain definition. I call such a protocol F robust for a certain function F if we can say the following. So there's a family of subsets of qubits such that whenever the Pauli error belongs to this set of Paulis, then the support must contain one of these subsets. This is similar to what I explained in the case of the repetition code. So we have a family of subsets, and an error basically means that we have a logical error means that we have a subset contained in this logic in this physical error in the support. Okay, and the second property is this. We need a combinatorial upper bound on this kind of quantity, and this is the function F. So this is what I call an F robust protocol. The notion is useful because if you have an F robust protocol, the function F gives you an upper bound for the failure probability for local stochastic noise. And the proof of this is simply the union bound, similar to before. So we like to have F robust protocols for functions F we know, and one construction we gave a while ago was based on the 3D cluster state, and this was of course pioneered by Rausendorf, Bravi, and Harrington. So they show that there is long-range localizable entanglement in this cluster state. A cluster state is a short-range entangled state, so it can be generated by a constant depth circuit. And we found a measurement pattern, which is somewhat interesting on the boundary. So you have these triangular shapes, and you use Pauli measurements of each qubits. And then you get a protocol which prepares long-range entanglement between these two qubits here. These two qubits are the only qubits that are not measured in the circuit. And we can show that this actually gives an F robust protocol. where the function is basically linear. Perhaps this doesn't sound very good in the context of error correction, because that means that the error rate on this EPR pair is basically the physical error rate. But I should emphasize that we get this physical error rate at a very long range. In fact, this distance is basically can be up to exponential in the number of qubits you have in these sheets, which you can think of as repeaters. So this is an F-robust protocol, and so we know it works against local stochastic noise. But it only creates a single EPR pair. And of course, we need many EPR pairs. So let me ask a different question about fault-tolerant preparation. So far I was discussing whether the state that you get is the desired target state. But we could also try to characterize the effective noise we get after applying the circuit. And so here's a different goal you could have in mind. So maybe you want to say that if you have a local stochastic error here, then what you get here is still local stochastic, perhaps with a slightly different parameter. This is not the same as saying that we are preparing the desired target state, but we are preparing the desired target state up to a local stochastic error. And if you use this in the context of fault tolerance construction, that's usually sufficient because we have techniques for dealing with local stochastic noise. So what is the relation between F-robust preparation and this notion of noisy preparation of a circuit, of a state? We have a relation which we formulate as a parallel repetition theorem. So this is the setup. Suppose we have a procedure, an F-robust protocol, which prepares a given target state. And for simplicity, let's assume that R is constant. So this is the typical case of interest. For example, R could be 2 if we try to generate an EPR pair. And now the question is, what happens if we want to generate several EPR pairs? So suppose we run this protocol in parallel, we run it twice. Then obviously this circuit will prepare 2 copies of this EPR pair. But the question now is, what happens when we have noise? And a trivial answer could be, well, if you have independent noise, then of course you get noisy, 2 noisy EPR pairs. But the interesting question here is, what happens when you have local stochastic noise that affects both circuits at the same time? And our claim is that in this case, the output is basically 2 copies of an EPR pair corrupted by local stochastic noise of strength f of p to the 1 over r. So again, remember r is basically constant, it's 2 in our case. And so what we get here is that the noise strength of this effective error is basically just a function of the noise strength of the original error here. And the function is exactly this f, which appears in the robustness of the protocol. So this is our main technical result. And why is this interesting? Well, it's interesting because it applies to any number of repetitions of this protocol. So suppose we try to generate 3 EPR states, then we can still guarantee that we get 3 EPR states with local stochastic noise, or 4, or any number of EPR states with local stochastic noise. And we can control the strengths of the noise we have here. So this is our main building block. So now we can generate many EPR pairs that are noisy, but we can control the amount of noise. And this preparation is in fact constant depth. So I can now put things together. So we are trying to go from a circuit which uses full connectivity and perhaps is noisy to one that uses only low connectivity. We use 3D. So we use this pairing algorithms. This was the basic idea. So we needed entanglement between such pairs. And the way we get this in a fault-tolerant manner is to use our quantum buses. So we use this construction with the 3D cluster state. We use 4 such cluster states in this case, and then we can entangle the EPR pairs we have on these boundaries using entanglement swapping. And in this way, we generate an EPR pair on these sites. So this is basically the idea. As argued before, because each of these protocols is F-robust, the joint thing will generate 4 copies of an EPR state up to local stochastic noise. And then you can do entanglement swapping. In this case, you only need 3 entanglement swaps, so it will propagate local stochastic noise to local stochastic noise. So in the end, you get constant fidelity bell pair. So that's the basic idea, but of course, we don't want to do this for a single pairing only. We want to do this in parallel for several different such pairings. And so we actually generate many EPR states with local stochastic noise. And then we need a kind of parallel repetition theorem for entanglement swapping that shows that if you have local stochastic noise, you get many copies up to local stochastic noise if you combine each of these 4 along a path. Okay, and with this we get our main localizer construction. So we start with an arbitrary quantum circuit on n qubits and depth t. We get a new circuit, a fault-tolerant circuit, which is slightly larger. It's 3D local. It has the same depth as the original one. This is important. And it simulates the original one exactly. And here's the key part. If you have noise in this fault-tolerant circuit, then this is equivalent to noise in the original circuit with a noise strength that we can control. So these constants are known. Okay, and now we can put this together. So as I said, using this localizer together with a fault-tolerance construction like the one by Yamazaki and Kohashi gives us a fault-tolerance construction using 3D local operations. So these are our constructions. We can also work in a quasi 2D architecture if you want. So this has dimensions n times log n, roughly, or square root of n times log n. But what's important here is that we get the same depth overhead as in the Yamazaki and Kohashi construction. And this is better, it's quasi-polylogarithmic in contrast to previous constructions, which all have a polynomial quantum depth overhead. I should say that these first constructions, in this context, I mean, of course, this is a problem that has been considered for some time. They all have a polynomial qubit overhead and a polynomial depth overhead. So these first constructions were based on using swaps to make things local. There's also nice work. I mean, a whole series of works. These are just a selection of references that start with the surface code and starting with the paper by Rasendorf and Harrington, and basically building up from this using, for example, lattice surgery more recently. And all of these use a polynomial overhead both in qubits and depths. Okay. Now, the other application we can give here is that of building a fault-tolerant quantum memory. So here, instead of fault-tolerant construction for computing, we use good quantum LDPC coders and a recently discovered decoder for such LDPC codes. And if you put this together, you can simulate an ideal quantum memory using a low connectivity noisy device. So in this case, for example, we can say that our work gives a construction that has a polynomial qubit overhead, and the quantum depth overhead is constant if you use this single-shot decoders for quantum LDPC codes. This should be compared to earlier work. So, for example, the work by Pattison, Krishna, and Preskill that is quite recent. They actually use a 2D architecture, sort of a bilayer architecture. They have a small qubit overhead, but basically because they use swaps, they get a polynomial depth overhead to get these memories. And of course, this overhead is also polynomial in these early constructions. Okay, so now we could ask, are our constructions optimal? And there are two bounds. One is a bound on the size of stabilizer syndrome measurement circuits for LDPC codes by Delphos et al. And there's also bounds on recovery maps for quantum error corrections in d dimensions by Baspin et al. And this is somewhat complicated because some of the bounds apply and sometimes they don't to different setups. So if we, for example, ignore all the constructions that don't involve fault tolerance, so for example, our routing protocols without fault tolerance, then we have this situation here. So the Pattison et al. Work saturates these bounds, but actually this Delphos bound doesn't apply because they don't have an LDPC code. And our work, we don't get saturation here, but here we get saturation, but the bound doesn't apply. But so I think in general this is an open problem of what the best construction is. But in terms of depth overhead, we believe that our work is perhaps close to optimal. I mean, maybe you can go from quasi-polylogarithmic to constant, but yeah. So there are different regimes. As I mentioned, the Pattison et al. They have polynomial depth overhead, but they can do things in 2D, whereas we need 3D and so on. I'd like to just briefly mention that there are, of course, other approaches to trying to make things local. And one that I find particularly interesting is the search for local codes. These are codes that have local stabilizer generators. And there has been quite some progress recently. So previously we had this converse results that are basically no-go results for certain parameter regimes. And thanks to the new LDPC codes, we now have new constructions. One that I particularly like is the one by Williamson and Baspin. So they use a certain kind of code concatenation, if you like, of surface codes to design codes. So you can take any CSS code, like the Shore code, and turn this into a new code, the layer code. And if this is applied to good quantum CSS codes, LDPC codes, then you get optimal parameters in 3 dimensions. Okay, so I should end here. So basically we have some new fault tolerance constructions, and I believe what could be useful in general is this idea of separating locality considerations from fault tolerance design, from the development of codes, and this can be done using these techniques. But we still have many open questions concerning optimality in particular. It would be nice to see whether or not similar constructions can be made in 2 dimensions that also have a low depth overhead. In general, I think our field has recently seen some very significant developments, in particular the discovery of quantum LDPC codes, the resolution of the so-called low energy trivial states conjecture, which is closely related to that, and the design of these optimal local codes that I just mentioned. So I think it's a really exciting time to work in this field. And with this, I would like to thank you for your attention. And so these are the 2 papers that I mainly talked about with my student, Xin-Ho Ke. So thanks a lot.
Great. Thank you very much, Robert. Do we have any questions for Robert? So I have a question. So you mentioned in this Yamazaki and Kawashi paper, they also consider the classical processing overhead. I was just wondering whether you've also analyzed that in this work, and whether that also applies here.
We haven't analyzed it, and in fact, so our decoders, I mean, we use minimum matching, so you have a polynomial time classical computation, and it's certainly not clear what happens if you take this into account. So, but so we're basically following the tradition of saying that classical computation is cheap and efficient, but yeah, of course, this newer work is really exciting because it finally also takes this into account. But I think we need different decoders and possibly even different constructions to address this here. So good question.
Okay.
So they use concatenated codes and not something like the surface code. So the decoders are quite different.
I see.
Can I ask a question?
Sure.
Please go ahead.
Is there any hope to make this into 2D? I mean, 1D in error correction and another dimension to routing for routing. Is it possible to make 2D local Fortran?
So I guess so we do have various trade-off relations, at least for the existence of codes in 2D. So some of them are shown here. So but I think there's neither a no-go theorem nor really a construction. I think if you want such low depth overhead, so I think we don't really know how to do this.
Okay, thank you.
I think it's an important problem. But as far as I know, like all the lattice surgery constructions, for example, using the surface code, they use a larger depth because you have to repeat syndrome measurements to get enough syndrome information. So I don't know. I will be interested in seeing more developments here.
I have a couple of questions. And the first one is very simple. In some table, you mentioned like Closai 2D.
Yes.
Yeah. What is Closai 2D?
So Closai 2D means that we have in one direction it's a bit thicker than. I mean, it's not L by L by 10L, but it's L by L by.
Okay. So something like it's a by layer is like definitely Closai 2D, but you have a little bit more.
It's worse than by layer. It's really log L, L by L by.
Log N. I see. Okay.
Yeah.
Thanks. And the other question is a little bit, high level question. Looking at your construction, I think there's some similarity to distributed quantum computation, where the graph is something different. You consider several parties who have small computers, and you want to perform some quantum computation together. Yeah. And my question is, do you think it's possible to apply your approach to this distributed quantum computation and get some interesting result? Because at least, at high level, it's quite similar because distributed quantum computation is just a matter of graph.
Yes, I mean,
So maybe you can apply, yeah.
Yeah, certainly it is a scheme for doing some kind of non-local computation efficiently or in a depth efficient way. But so in that sense, I think it can be directly transferred, but the fault tolerance part is perhaps less natural, no? Because you will need you will need sort of an array of qubits in each side. Well, I mean, you could think of this, but the architecture is more naturally really a 3D grid if you think about the cluster state. So
that's right. Yeah.
So that part is perhaps less natural. But if you just talk about the qubit routing questions, then that's obviously connected to non-local multi-party computation. Yes.
Okay. Yeah. Thanks.
I have one more question, which is, do you know anything about the experimental progress on like 3D architecture? I know 2D is very popular, but like what kind of experimental platform would you envision this could be implemented in?
I'm afraid I'm not too familiar with such efforts. I mean, as far as I'm aware, this is perhaps not done extensively, except maybe in photonic architectures where the third dimension is the time. There are, of course, approaches, but that's perhaps different. So here you really need a 3D architecture, ideally. But perhaps you can somehow couple the current 2D architectures to each other to get this. But yeah.
Okay.
Maybe I'm not the right person to ask this question.
No, that's fine. Do we have any other questions for Robert? Okay, well, if not, then yeah, thank you again for the great talk.